And let's go ahead and begin. This is about where we left last time. I was trying to convince you, and we spent probably more time than we should have looking at a couple of simple examples. If you let me back up, I made up a couple of little monitor problems, and we talked through them, and then we talked about some different monitor behaviors. Remember the idea of a monitor? Sorry, now I have to go through this animation. The idea of a monitor is well, as we'll see later, it can do the same kinds of things that semaphores do. It's just packaged a little bit differently so that some simple mistakes that you might make with semaphores, you can't really make with monitors, because some of the basic synchronization behavior monitors do automatically for you. The idea, and I know I'm repeating myself from the other day, but I'll try and say it real fast. Monitors can have state, and the state is automatically encapsulated within the monitor. You can't get to the state without going through one of the monitor's functions. And only one thread at a time can be running inside a monitor's function. So if you're in the middle of a monitor, a function on a monitor, you don't have to worry about other code, other threads messing with that shared state at the same time. We had just introduced the idea of a condition variable. And that is, it's kind of the one extra thing we need in monitors to make them able to solve as many synchronization problems as semaphores. We need some way of, even after you've entered a monitor function, being able to temporarily step outside the monitor because you weren't able to do the thing you were trying to do. And here's another example of that. This is a kind of a well, it's the dining philosopher's problem. So it's a problem you're already familiar with, and it's a little bit bigger than the two we were just looking at. The idea is we're going to try to build a monitor that does the synchronization behavior of the dining philosophers. So when a philosopher wants to eat, they'll call this start eating function. And then when that returns, we'll write the monitor so that that means it's okay for them to start eating. It's on our next page, and we'll talk about these in more detail, but once you're done eating, you're supposed to call this finish eating function. And then that lets other philosophers know that if they were waiting to start eating, that maybe it's okay for them to start now. You can see this monitor has an initialize function, and we said monitors can have that. It's kind of like a constructor for the monitor. The point of a monitor, at least the point of packaging synchronization like this, is if we can have a programming language that knows about constructs like monitors for us, then it can do some of the work of writing synchronization code for us. So I talked through this, at least I got barely started talking through this last time. So let me say again what we've got. We'll pretend we've got 5 philosophers, and for each one, we got a flag that says whether they're eating or not. So whenever a philosopher, in fact, you can see it down at the bottom of this slide, whenever they start eating, right before they return from this function, they set that flag to true. So that keeps up with which philosophers are eating and which ones aren't. And if a philosopher wants to eat, they're going to need to look at the 2 philosophers on either side to decide whether or not they can. And that's, I just lost power. All right, I think we're back recording after a brief power interruption. Yeah, so I think everyone can see my screen. So I was talking through the state of this monitor, and I'll try to hurry on ahead. So we talked about this eating flag, and if you look down at the initialization function for the monitor, that's what it initializes after, yeah. We make all of these eating variables, but we have to set them all to false. So initially, none of our philosophers are eating, and that's all the initialization function does. This condition variable, or really this array of condition variables, is our way of making philosophers wait if they can't eat right now. Well, let's talk about that while we were talking about this start eating function. So if you're philosopher number I and you want to start eating, you look at the 2 philosophers on either side of you, and that's what this while loop is doing. I look at, if I'm philosopher I look at I plus 1 mod by p count, so wrapping around at the end of the table, and I look at the philosopher on the other side, essentially I minus 1 mod p count. And if either of those are eating, I have to wait. Instead of busy waiting, which we agree we don't want to do that, I'll use this condition variable. So, and this is exactly what I'm trying to talk about with condition variables. I got inside the monitor, I had to get inside it just to be able to look and see if my 2 neighbors were eating. Once I got inside, and if I noticed one of them was eating, I'll temporarily give up the lock on the monitor and wait on this condition variable. And every philosopher has a condition variable that they use to wait on. So if I can't eat yet, I wait on one of my condition variables. Once I finally get a chance to eat, hopefully someone's going to wake me up by signaling on my condition variable. We'll see that on the next slide. I set my eating flag to true, and then that philosopher can start eating. So this kind of shows how philosophers block, or how they go to sleep if they can't eat right now. This is the other half of that. When a philosopher is done eating, well, they set their flag to false because they're not eating anymore. But what if one of their neighbors was waiting on their chopstick? They signal on the condition variables for both of their neighbors. In class, I usually illustrate this by saying, well, it's kind of like they poke the two people on either side of them. And if either of them was sleeping, waiting for them to give up one of their chopsticks, that wakes them up, backing up a slide, gives them a chance to go back and check this condition on the while loop. And if now both of their chopsticks are available, they get to eat. Otherwise, they go right back to sleep until their other neighbor finishes eating. So this gives us, this is one of the solutions we talked about earlier when we first saw that we had a deadlock problem with dining philosophers. We said, how about if you only pick up a chopstick if you can get both of them? And that's kind of what this does. Up here in the start eating, we look, and if we can get both of them, we go ahead and get them. If we can't, we wait for one of our neighbors to wake us up. And then the neighbor makes good on that. When they finish eating, they poke us by signaling on our condition variable and waking us up. I've made this point before, but I think this is a good place to make it. Notice here's why it's good that condition variables don't maintain a count. They're a little bit like semaphores, but if you release on a semaphore, it remembers that it was released, and then later someone can acquire on that. But here, if we finish eating and we poke our two neighbors, we signal on their condition variables, and let's say they weren't waiting, well, no harm done. That signal just gets ignored if no one's waiting on that condition variable. So this solution, it's better than some of the ones we talked about. It would let multiple philosophers eat as long as they can have the chopsticks they want. It should be deadlock free, but, and I think we said this before, there is a risk of starvation in this solution. Even if philosophers, if they started eating and they always eventually finished eating, it's still possible that you might be stuck between two philosophers that really like to eat. And if one of them was always eating, even if it wasn't the same one, you might never get a chance to eat. I point this out because it's our first non-trivial use of condition variables. It lets us implement, I think, a clever solution, but one that has the hazard that philosophers could starve. Any questions? So the next thing we're going to do is, just like we did with semaphores, we're going to talk about two APIs for working with monitors. We've got two implementation languages, so we're going to learn how to write monitors in each of those. Any questions before we move on and do that?
I don't understand how it works while they're only waiting on one chopstick. Wouldn't they have to wait for both of their chopsticks?
A picture would make this easier to talk about. Then we could look at the code and I could kind of point around on the picture. So let's say you're philosopher number 0 and you go into start eating, and philosopher number 1 is already eating. So you're going to notice that they're eating. What the other guy is doing doesn't really matter because you already detected one of your neighbors was eating. So you're going to go to sleep on your condition variable. Philosopher 1, did I say that? You're philosopher 0, philosopher 1 eventually finishes eating. They call this finish eating function. They mark themselves as no longer eating. And then, well, if they're philosopher 1, right here is where they wake you up. This I plus p count minus 1. The reason, so essentially I'm trying to say I minus 1 mod by p count, but the behavior of mod can vary depending upon implementation language. So that's why I'm doing this trick of adding to it before I subtract 1. But this is where they signal on.
Wake up.
Sorry, go ahead.
So the wake up is only telling them that now is a good time to check for both chopsticks again.
Yes.
I guess.
When they do the signal on condition variable 0, backing up, that's going to wake up philosopher 0. Philosopher 0 will go back. So once philosopher 0 is runnable, they'll go back, look in the condition again, and if both of their chopsticks are available, they get to start eating. So I think of this condition variable as waking up, as an efficient way of waking up the philosophers who care whenever a philosopher finishes eating. If I finish eating, someone way across the table from me doesn't care, but the two philosophers on either side might. So I wake them up if either of them was asleep. I said a lot there, so hopefully I got the answer to your question. Is that good enough or anything else?
Yeah, it checking again in the while loop was what was confusing me slightly.
Yeah, and I guess you could still get in that situation where one of your neighbors finished, but the other had started eating, and then when they finished, the other one had started eating. So you might keep getting woken up, but never be able to make progress. And that's really the starvation possibility that we're talking about down here. Any other questions before we start looking at some APIs? So I said we got two ways we're going to do monitors. Java's going to be the easier one. But first we're going to do, if you're programming in C on a POSIX system and you wanted to write a monitor, how could you write it? Well, there's an API available for writing monitors in C, but unfortunately it's not built into the programming language. I think the best idea of monitors is if we made the programming language know about some synchronization primitives, we could get the compiler to do some of this for us. But it's too late for C as a language. It was designed before we were thinking about things like this. So you can still build something that works like a monitor. It's just the language doesn't really help you out. You have to do everything yourself. So you still have to remember to make all the calls that you might make if you were using semaphores. You can still think like you're building a monitor. You can think like, well, when I do this, I'm entering the monitor. It's just you have to write that code yourself. All right, so how do you build a monitor in C? There are really two things you have to use. One of them is a mutex. That is the thing that you use for entering and leaving the monitor. The idea of a monitor is normally, well, whenever you enter one of its functions, you enter the monitor automatically, but C doesn't do that automatically for you. So if you want to write your own code that says, here's where I'm entering a monitor, you're going to have to make a variable of this type, pthread mutex t. And I just called it lock. And again, I think of that as the door for entering and leaving the monitor. And then whenever you want, well, I'll skip down to what I was saying. Whenever you want to enter the monitor, you call pthread mutex lock, and then you pass the address of that lock variable. So if your monitor was a bunch of functions at C, in C, you'd probably do this on the first line of every one of those functions. And then when you leave the monitor, pthread mutex unlock, and you pass it the same address of the lock variable. So if you thought of your monitor as a bunch of functions, whenever you left one of those functions, you'd want to make sure you called this to give up the lock on the monitor. I'll mention that's an easy place to make mistakes. And that's why a real programming language supported monitor is probably much more convenient, because you only enter a function in one place at the top. But depending upon how you write your functions, you may have several places where you could leave the function. And if you always acquire your lock on the way in, you need to make sure that you remember to release it every time you leave, even if there are many places. So you might need this line of code every time you return early from a function and down on the last line of the function. So again, think of this as the lock for the monitor that you acquire when you enter it and release when you leave it. I skipped this stuff up here. Before you can use a mutex variable, you need to initialize it. There are two ways to do that. The hard way is you could call pthread mutex init, give it the address of the lock, and it will initialize that lock so that now you can use it. Or there's a constant, a preprocessor defined constant. And when you declare the lock, you can initialize it to this constant, and then you don't have to do the pthread mutex init. So if we didn't need condition variables, we'd be about done with monitors for C, because we talked about how to acquire and release the lock on the monitor. But to solve larger, trickier synchronization problems, we do need condition variables. So just like we're pretending for monitors, you can have as many condition variables as you want. We just saw that Dining Philosopher solution where we had 5 condition variables, one for each philosopher. For every condition variable you want to make, you're going to need make a variable of type pthread cond t. Just like the mutex, before you can use it, maybe in main or something like that, you're going to initialize it with pthread cond init and give it the address of that condition variable. Or just like a mutex, there's a constant you can assign it to when you declare it, and then you don't have to make this init call. And then once you've made a condition variable, how do you use it? Well, we need two operations. You have to be able to wait on that condition variable. Here's how you do it. Pthread cond wait. Wait is a little unusual in POSIX semaphores because you have to give it two things. You have to give it the condition variable that you want to wait on. So I want to wait until someone signals on this condition. And you have to give it the lock for the monitor you're running in. This makes some sense because when you wait on a condition variable, the thread that does that automatically blocks. So it automatically waits on something, and it gives up the lock on the monitor so that eventually some other thread can enter the monitor and wake it up. So when you wait on a condition variable, you want to block and you want to let some other thread in. And this function needs both of those parameters. If you're waiting on a condition variable, you should already be running inside a monitor. You should have already acquired the lock on this mutex. So you give it the condition variable you want to wait on and the monitor, the mutex that you want to give up the lock on. The other call, pthread cond signal, is just like the signal call. It wakes up one thread that's waiting on this condition variable. If there are no threads waiting on this condition variable, it doesn't wake up anyone. We got one extra call for POSIX semaphores. For our pseudocode, we're not assuming that we have a broadcast, but in reality, it's pretty common for monitors to support a signal operation that wakes everyone up. And that's what this last one does. Pthread cond signal just wakes up one thread if there are any waiting threads. Pthread cond broadcast wakes up every thread that's waiting on this condition variable, and then they can each wake up and look around to decide if they can make progress or not. Again, I wouldn't generally assume that you can have a broadcast. That's why in our pseudocode, we're pretending we don't, but it is common to have that kind of thing. The reason I say you might not want to generally assume you have it is if you write your code and you assume you've got a broadcast, then you're going to have to fix that code if you try to run it on a system that doesn't support broadcast. So that's what it takes to build a monitor in POSIX API. I wrote a little monitor to try to show this off, so I'm showing off the same API we just looked at. Instead of making up a new problem, I just used the bounded buffer producer consumer problem because we're already familiar with that. So some of the state looks the same. You've got a buffer with room for 10 items. Your buffer is implemented, in this case, as an array of ints. So every time I put an item in the buffer, I'm just going to add an int to it. And I've got two fields for keeping up with how much stuff is in the buffer right now and where it starts. These next three variables are my condition, are my synchronization variables. This first one is my mutex. So whenever I enter or leave the monitor, I'm going to use that. I called it mon because I think of it as entering or leaving the monitor. And then for bounded buffer producer consumer, it seems like there are two things threads might have to wait for. I might have a producer thread that's waiting. If the buffer's full, it has to wait until there's an empty space in it. So I'll make one condition variable for that. That's the second one here. I think of it as I'm waiting for an empty slot. If I'm a consumer, same idea. If the buffer's empty, I have to wait for someone to put a buffer or an item in the buffer. So I'll have another condition variable for doing that. The nice thing about having these two condition variables is I can make my monitor more efficient. If I just took an item out of the buffer and maybe there was a producer waiting for an empty space in the buffer, I can wake up a producer. Same thing the other way around. If I just put an item in the buffer and maybe there was a consumer waiting for an item to show up in the buffer, I can use this condition variable to wake up just a consumer. So here's the state of our monitor. Here's main. So this, for a POSIX monitor, this is kind of like where we get our chance to initialize it. I'm going to make a couple of threads. One's going to be a producer and a consumer. The code for them is on the next couple of slides. So I'll create each of those. And then once they're done, I'll just wait for them to finish. So nothing too fancy here. For the producer, I'm going to, and this is just a pretend application, but I'm going to pretend I'm producing 1,000 items. On each iteration, I'm going to pretend my loop control variable is the number I just produced. So I print out a message, and then this bluish code that I put here, I think of that as being the code for my monitor. Here, I didn't go put it in a separate function. I just put it right inside this function, but I think of entering the monitor on this first line, and I think of leaving it on the last line. I just put it in the caller's code rather than putting it in a separate function. How does it work? Well, like I said, whenever you want to enter the monitor, you acquire the lock on a mutex. And then, if I'm a producer, I have to worry about, well, maybe the buffer's full. Maybe there's no room for the item I just wanted to put in. So I check that. If the buffer's full, I wait on the condition variable we just talked about, the one that's waiting for an empty slot in the buffer. I use that condition variable, and like I said, I have to pass in the monitor because this function's also going to give out the lock on the monitor at the same time. I did this with a while loop, just in case. So if someone wakes me up and then by the time I get to run, someone else took the space I was going to use in the buffer, this while loop will check that condition again before it goes on and puts something in the buffer. Once there's room in the buffer, I put it in, and that's just variable manipulation. When we did our semaphore-based solution to this, we had to worry about, well, what if some other thread is messing with the buffer at the same time I am? But we don't have to worry about that here. We locked out all the other threads up here when we acquired the mutex. And then even if we went to sleep here, before we resume running inside the monitor, we're automatically going to reacquire the lock. So when someone signals, we talked about this with signal and continue. When someone signals and wakes you up, well, if it's signal and continue, they get to resume running, and before you get to run in the monitor, you end up having to reacquire the lock on it. That automatically happens, but that lets the first thread, the signaling one, get out of the monitor before you get to resume running in the monitor. So put something in the buffer. We don't have to, like I just said, we don't have to worry about race conditions right here. And then on my way out, the same thing that I just said. What if there was a consumer waiting for an item and I just put one in the buffer? Let's wake up a consumer just on the off chance there is one. So I signal on that other condition variable that we're using to block consumers. And now I'm done with the monitor. So I give up, I unlock the mutex, and I go back around and produce the next item. The other half of this code is the consumer code. And it's kind of like with the semaphore solution, it's kind of symmetric compared to the one we just looked at. For 1,000 iterations, I'm going to get an item out of the buffer and then print it out. So to get an item out of the buffer, first I lock the monitor so no one else can mess with it while I'm looking at it. And then if the buffer's empty, I had to lock the monitor before I could even look at whether it's empty or not, because I think of even this num variable is part of the state of my monitor, and I want to protect that state with mutual exclusion code. So I locked everyone out. I looked, and if the buffer's empty, I'll wait until an item arrives. Here is what I just said on the previous slide. I'm waiting on this item condition variable. That's the one that gets signaled at the end of the producer code. When an item arrives in the buffer, we wake up any consumer that might have been waiting on an item. So once there's an item in the buffer, I get it out, and that's just variable manipulation. And then before leaving the monitor, I wake up a producer if there was one waiting. Same idea here. Maybe the buffer was full and there was a producer waiting on an empty slot. I just took an item out, so there must be an empty slot now. I'll signal on this slot condition variable to wake up a producer if there was one. And like I've said a couple of times, if there wasn't, no harm done. If no one's waiting on a condition variable, the signal doesn't do anything. All right, that was a long-winded explanation of this monitor, but it shows the POSIX API for writing monitors, where we've got, we don't really have direct programming language support, but we have these types of variables and these function calls we can use to build a monitor. Any questions before we go on and talk about the Java API for monitors? All right, let's give Java a try. I said that in C, monitor support is not as nice as it could be because they designed the language before they were really as worried about multi-threading and synchronization. In Java, it's the other way around. When they built this language, they knew they were going to have to worry about threads and synchronization. So they built some features for that right into the syntax of the programming language. Even if you had never done threads in Java before this semester, you've still seen some of this stuff because it shows up all over the place in the API. I said a couple of times, a monitor is kind of like an object. The data, the fields are protected, and you can only access them if you go into one of the functions on the monitor. And that sounds a lot like an object with methods that you have to call to access the fields. And that observation was not lost on the people who designed Java. They built the language so that every object, or any object you want, can work like a monitor. All you have to do with that to make an object work like a monitor is you've got to put one or more functions, one or more methods in it that are marked as synchronized. You probably, like I said, you've probably seen this all over the place in the Java API. The word synchronized there means I want to, well, let me say, every object can have a lock associated with it. And if you start using an object like a monitor, you're using the lock on that object. And all the word synchronized here means is acquire the lock on this object before entering this method. Sticking the word synchronized there automatically gets the compiler to do that for you, so you don't really have to, you don't have to write code to acquire the lock, other than what I said here. Another nice thing that I said, another nice thing compared to C is Java will write code to automatically give up the lock when you leave this method. So even if you've got multiple returns from this method, you don't have to worry about forgetting to give up the lock. Java will take care of that for you. So here's how you could build a monitor that didn't use, that didn't need condition variables. We'll talk about that next. First, let me say there's one other syntax for acquiring the lock on an object. Probably the most common way is what I just showed back here. A synchronized method automatically acquires the lock on the object that it's in. You can have multiple synchronized methods, and then each of them will acquire that lock before it enters. So only one thread at a time can be running in a synchronized method. Or you could do this trick. This is called a synchronized block. And if you need to access the lock on an object, or you need to access shared data in an object, and you just want to acquire the lock without entering an object, you can just put the keyword synchronized inside any code. And then as a parameter after that, you can pass in the object you want to acquire a lock for. And this will acquire the lock on whatever object you ask it to. I've got a term down at the bottom of my slide that's going to make this a little easier to talk about. In Java, they use the term entry set to mean the set of threads that are waiting to get the lock on an object. So if you have a synchronized method and one thread, and you try and call it, and some other thread already has the lock on that object, then you have to wait. The entry set is the set of threads that are waiting for that. Here's a picture, I think, out of your book that shows a way you can think about this. If you think of this little egg-shaped thing over here as a monitor, for Java, whenever a thread calls a synchronized method, it acquires the lock on the monitor, and any other thread that tries to call it before it has given up that lock, they all go in the entry set. They have to wait until the owner of the lock gives it up, and then one of them will get picked to acquire the lock. I'll go ahead and say this. The language I used there, I tried to pick carefully because Java doesn't make guarantees about who's going to get that lock next. If one thread has a lock and there are 4 other threads waiting to enter a synchronized method, when the owner gives up that lock, Java says it will pick one of those threads to get the lock next, but they're not necessarily in queue order. The definition of the Java virtual machine lets you have any rule you want for picking that. And that means as the programmer, you have to try to make sure that your code is going to work, that it's going to be correct. even if these threads are not chosen in queue order. All right, so we know how to build a monitor where we get mutual exclusion. It's almost trivial in Java. But we need one more thing to solve larger synchronization problems, and it's the same thing we talked about before. We need something like a condition variable. And Java has something like a condition variable. It's not as flexible as what we've been talking about. It's not really as flexible as the mechanism provided by the POSIX API, but it's readily available, and as long as it has some performance disadvantages. And as long as those aren't a problem for your application, then this is an easy-ish way to build a monitor. So how do condition variables work? Well, all objects have a lock associated with them. To get into a synchronized method, you have to acquire that lock. But once you're in a synchronized method, you can temporarily give up that lock and wait for something. And the way you do that is with the .wait method. So if you're running inside an object, inside a synchronized method, and you want to give up the lock and wait for something to happen, you can call wait on that object. So if the object was X, you could call x.wait, and that will do what I've just said. You will temporarily give up the lock on the object, and you will wait for something to happen. Java describes this as you will go into the wait set. Let me see if I've got a picture. It's a couple of slides ahead, but let's go ahead and look at it. So every object that you're using like a monitor kind of has potentially two sets of waiting threads. The entry set are the threads that are waiting to get into the monitor. They probably called a synchronized method, and they're waiting for whoever has the lock to leave. The wait set, those are the threads that already got into the monitor, but they couldn't finish what they were trying to do. They got in, they looked at the state of the monitor, and they said, oh, I have to wait for some other thread to do something. So they called wait on the object, and they went in the wait set. And they're going to stay there until, backing up a couple of slides. So .wait puts you in the wait set. You give up the lock on the monitor. .notify is like Java's version of signal. It's how you wake up when you call .notify. It wakes up one thread in the wait set and puts it back in the entry set. So it wakes it up so it's runnable again, but because it's back in the entry set, it still has to reacquire the lock on the monitor before it can resume running. And that makes sense. That's the same idea as the signal and continue policy we talked about. If you come along and call .notify, that wakes up a thread, but it goes back into the entry set. So you get to continue running in the monitor until you give up the lock. And then one of the threads in the entry set gets to resume running in the monitor, or gets to enter it or resume running. So I think I can say this faster now. If you call .wait, you go into the wait set and you block. If you call .notify, one thread from the wait set gets put back in the entry set. If you call .notify all, that's kind of like a broadcast. In Java, that wakes up every thread in the wait set and puts them all back into the entry set. The reason Java does it this way, and I kind of hinted at that before, is whereas with monitors, we've generally been assuming you can have as many condition variables as you want. So if there's a new thing a thread might be waiting for, like items in a bounded buffer or empty space in a bounded buffer, you can have a condition variable to wait on that thing specifically. But in Java, this wait notify behavior is kind of like one giant condition variable. And anytime a thread in a monitor needs to wait on something, it's probably going to be waiting on that one giant condition variable. When you wake up a thread that's waiting, well, you don't have a way of doing it selectively. You are going to wake up any thread that's waiting on that condition variable. If there might be multiple threads waiting on a bunch of different things, realistically, you might have to wake them all up and just let them decide if they're the one who can make progress or not. So notationally here, I wanted to show that wait, notify, and notify all are all methods on an object. In fact, even in your first days of learning Java, you probably saw the object class, the root or the highest superclass in the inheritance hierarchy. And up there on object, there are a few methods that every object has. And these were 3 of them. Even in the earliest days of Java, you could go back and see that the object that you looked at had these 3 things on it. But the way you would use them typically looks more like this. They are methods on an object, but if you're running in a synchronized method on an object, so you've got some class, you've got a synchronized method in it, you get into that synchronized method and you realize you have to wait, you'll probably just call wait, because that'll automatically call it on the object you're running in. So when you see wait used inside an object, it's probably going to look more like this. Same thing with notify. If you're inside a synchronized method and you want to wake up a thread, you'll just call notify and that'll wake up one thread in the wait set and put it back in the entry set. In fact, in Java, it's probably going to look more like this. Because like I said, if you might have a bunch of threads waiting on some condition, waiting in the wait set, and you can't necessarily wake up just the one thread that you want to wake up, you might have to settle for waking them all up. And then those, and this is kind of what I was saying before, if I got woken up and I realize I can't do the thing I wanted, I can always go right back to sleep and wait for someone else to wake me up. So this is what condition variables, this is what monitors look like in Java. And you can see, at least with syntax like synchronized methods and with objects automatically having locks on them, we've got good programming language support for writing synchronization code. We already looked at this picture. We're going to look at an example of a monitor in Java. Questions before we do that? All right. I wanted to mention, I feel like I talked down about Java a little bit because its mechanism for monitors doesn't let you have arbitrarily many condition variables, so it could be a lot less efficient. But there's a way of getting around that. It's really just this built-in mechanism that's built into the programming language that has that restriction. Java also has support for monitors that can let you have as many condition variables as you want. I've listed some of that stuff here. Notice it's in the same package that we looked at before, java.util.concurrent. And a reentrant lock is a way of building a monitor yourself using these objects. A condition is a interface that, and there's a factory method on reentrant lock that will give you as many condition variables as you want. So if you needed to selectively wait on something, if you were in a monitor and you needed to wait and you wanted to be able to selectively wake up waiting threads, you could build it with this. We're not going to do that in this class. I just wanted to mention that Java does have more, potentially more efficient ways of building monitors. I wanted to show a implementation using the Java API for monitors. I think this code is posted on our Moodle page if you wanted to try it out yourself. For the slides, I broke it up into a couple of slides, and we'll talk through it real fast. It's a lot like the C solution that we looked at before. So that's going to let us go a little bit faster. Here's the state. It's all fields of this bounded buffer object, and it's the same as we had before. I want space for 10 items in my buffer. I made the buffer an array of objects so I can put whatever I want in it. And I'll use the same fields for keeping up with what part of that buffer is full and what part is empty. This is kind of my producer code. The loop for the producer isn't here. But instead of, well, I guess whenever the producer produces an item, I'm going to have him call this method to put it in the buffer. So it's kind of like I'm building a little object that implements the bounded buffer behavior. So when a producer produces an item, they call insert item. Notice I made that a synchronized method on this object. So whatever thread tries to call it will automatically acquire the lock on the object. If I'm a producer, first thing I have to worry about is there space in the buffer? So I've got a little loop here that says, if the buffer's full, call wait. And that's that same thing we were just looking at. That puts me in the wait set. Essentially, it makes me block until someone else notifies to wake me up. So I might run around this while loop a few times until there's space, or until there's empty space in the buffer. Once there is, I put a new item in the buffer, the item that just got passed into this function. Same as before, since I'm in a synchronized method, only one thread at a time should be running in any synchronized method on this object. So I don't have to worry about other threads messing with the buffer while I am. And then on the way out, same as our other solution, I start to think, well, maybe I just put an item in the buffer. Maybe there was a consumer waiting for that item. If there is, let's wake them up. Here I do that with notify all. And here's kind of what I was talking about the potential performance disadvantages. That's going to wake up any thread. Even though I'd like to just wake up a consumer, I'm just going to wake them all up, and then they can decide if they can make progress or not. Our next slide is the consumer version of this same method. And this while loop is what I was just talking about when I said they can decide if they make progress or not. Let's go ahead and talk about it. Up here at the top of the remove item code, the code called by the consumer, if the buffer's empty, I wait for someone to put something in it. Whenever someone does a notify or a notify all, when they do a notify all, they're going to wake me up. If the buffer's still empty, I'm going to ride around this while loop one time and then go right back to sleep. So this mechanism for waking up threads gives us a mechanism that's not that hard to use. It's just you may end up waking up threads that you didn't really want to wake up. All right, I skipped over this part so I could talk about the other, but obviously this is another synchronized method on our bounded buffer object. You call it when you want to get an item out of the buffer. This loop we just talked about waits until there is an item in the buffer, and then I get the next item out of the buffer. On my way out, I do the same thing. If I just took an item out of the buffer, maybe it was previously full. Maybe there was a producer waiting to put an item in the buffer. So let's wake them up just in case. This is gonna wake up any thread waiting in the wait set for this object. But if there was a producer waiting to put an item in the buffer, this will wake them up and let them know that there's now room for that item. I don't have a slide for main, but main makes a couple of threads and has it call these functions. So like I said, I think this example is posted. So if you want to take a look at the rest of it, it should be there and it should work for you. Any questions before we talk about one more classic synchronization problem? So we'll finish by talking, or at least we'll finish this section of the material by talking about one more classic synchronization problem and looking at really a couple of little monitor-based solutions for it. Our last one's called the readers-writers problem, and it's based on the observation. I mean, normally we talk about shared variables and we say you never want two threads accessing the same variable at the same time. But that's only sort of true. In general, it's okay for two threads to read a variable at the same time, as long as neither of them is trying to change it. Now, for regular variables inside a program, it's probably inefficient to try to lock down whether you plan on reading or writing, but for some applications, like database applications, you might want to make a distinction between whether a concurrent process or a thread just wants to look at a field in a database or maybe wants to change it. The readers-writers problem lets you give out two different kinds of locks based on what you plan to do. And up here at the top is what I just said. It's okay for two threads to read concurrently, but we don't want two threads to try to write to the same thing concurrently. And we don't even want to mix. We don't want some of them trying to read while others are trying to write. So we're going to build an object that gives out locks that way. When you go to this thing, you can say, I want a lock for reading. And it's okay if there are other threads that already have a lock for reading. But if you say I want a lock for writing, it has to make sure that there are no other threads that already have a lock for reading, that already have the thing locked for reading, and no other ones that already have it locked for writing. That's what I'm saying down here at the bottom. If we had a count of the number of writers that had a lock, and we had a count of the number of readers that had a lock, we would need to make sure, well, this is our safety condition. What it says is either there are no readers or there are no writers. So that would mean you've only got one type of thread. You don't have a mix of readers and writers. And either way, there better not be more than one writer. And I think that matches what I've been trying to say up here. It's just a lot more succinct here. And this is something that we could turn into code. So we're going to write a little pretend monitor that implements this kind of locking behavior. We're back to using our monitor pseudocode, but we could easily turn this into a Java or a C-based solution. So just like we said, I'm going to have variables that do what I just said. I'll keep a count of the number of readers and the number of writers who have locks right now. Now, we just said, well, I better not have both of these counts non-zero at the same time, because then I've got a mix of readers and writers, and this one, number of writers, better not get bigger than 0. And we'll implement that in our monitor. We'll have two condition variables, and I marked them here the way I'm going to think about using them. If you're a reader and you want to acquire a lock, you might have to wait if a writer already had a lock. So this readable condition is how readers will wait until it's okay to read. Same thing with this other one. If you're a writer and you want to get a lock for writing, you might have to wait. This condition variable is how you're going to wait. So we'll use that to put threads to sleep when we have to, and to wake them up when we can. So I mentioned there are two kinds of locks that we're going to give out. And these are the functions for how we're going to give them out and let them, and how threads are going to get that lock and give it back later. If you just want to read from whatever the thing is from the database field, you'll call lock reading when you want to acquire a read lock. And when it returns, then that means it's okay for you to read. When you're done reading, you'll call unlock reading to give up that lock. And looking ahead, we got the same two things for writers. When writers want to get a writing lock, they'll call this top method, top function. When they want to give up that writing lock, they'll call this bottom one. Let's talk through the reading functions first. So we're pretending these are functions in a monitor. We're pretending we're using pseudocode, so we don't have to put the word synchronized here like we would in Java. It's just understood that you acquire the lock when you call this function. So if you call lock for reading, you want to get a reading lock on the object. So the only thing you have to worry about is there better not be any writers who already have a lock. So that's what we check. If the number of writers is positive, we wait until it's okay to read. This is that readable condition variable we looked at. And even if someone wakes up, we still check that condition again before we give out the reading lock. Once it's okay to read, we count one more reader. So we increment the number of readers. And the real reason we need to do that is as readers acquire the locks, that's okay as long as there are no other writers. But as they give them up, we need to know when the last reader gives up its reading lock, because that's when it's going to be okay to write again. So down here, when a reader gives up their reading lock, they say, I don't need to read that thing anymore. We decrement the number of readers. And if it hits 0, then it's okay to write. So if there was a waiting writer, we wake up one waiting writer. Here's a case where we definitely wouldn't want to use broadcast because only one writer at a time can write. So if we knew the last reader just gave up their lock, it's okay for one writer to go ahead. Like I've said a couple of times, if there weren't any waiting writers, this signal does nothing. But if there was, this wakes up one of them and gives them a chance to write. Questions before we look at the writer code? So this is kind of the first half. Here's the job that the readers do. Writer code is a little trickier because if you lock for writing, you have to make sure there are no readers and no other writers. So we check that. As long as there's some readers or some writers, we wait until it's okay to write. And then once we give out our lock, or once it's okay to write, we increment the count of the number of writers. Like I said before, we don't really need to do this with a count. We could have done it with a Boolean because there should never be more than one writer, but it's easy to code and to talk about if we just treat it as a count. It's just a count that should never be bigger than 1. When they unlock for writing, we decrement the number of writers, and we could have an if here, but if you decrement it, it's got to be 0 after this because you never should have had more than one writer. So this must be the last writer giving up their access. Well, now we know there are no readers and no writers, so it's okay for either of them to go ahead. So we wake up, well, we give them each a chance. If there was a waiting writer, we wake them up. If there was a waiting reader, we wake them up. So this is our first stab at a solution. It's okay. I think there are two things that would be worth fixing in it, and we're gonna fix the easier of those two. I know that's a vague question, but does anyone see anything worth fixing in this solution while we're looking at it? I tried to hide it by lying to you a moment ago. And the place where I lied is down here. I didn't really lie, I just said it in a way that was a little misleading. If the last writer leaves, well, now it's okay for another writer to go ahead, or it's okay for a reader to go ahead. Well, it's not just okay for a reader to go ahead. If the last writer just gave up access, then all the readers could go ahead. So this we could replace by broadcast if we wanted. When the last writer gives up access, all the readers could go ahead and have access if they wanted. If we pretend we don't have broadcast, and we said in our pseudocode, we're pretending that we have to get by without broadcast. And some of that is because it's usually really easy to get by without broadcast. We already saw the trick for doing this. When we signal a reader here, well, that will wake up just one reader, but we could change the lock for reading function so that every reader just wakes up any other reader that might be waiting behind them in line. So whenever a reader gets access, we can just signal on readable again, and that'll automatically, it'll kind of cascade through the readers. When a writer leaves and they wake up one reader, each of them will wake up the reader behind them. That was the part that's easy to fix, adding one line of code to make sure it wakes up all the readers at once, or at least whenever it becomes readable. The other problem is this solution could starve writers. It's really the same kind of thing we talked about with the dining philosophers problem. Even if readers were coming and going, they would get access for a while and then they'd give it up. As long as there were always some readers wanting to have access, a writer might never get a chance. I guess backing up a slide or two, it's possible this number of readers count. Once readers started coming in, it's possible it might never drop to zero, in which case writers need that to get access, so they could end up waiting forever. There are ways to fix this. We could make it so that if you are a reader and you want to get access, but there's a waiting writer, then you have to let at least one of them go first. And in monitors, since you can have as many fields as you want, you can have as much state as you need to, you can build solutions that really do work like that try to be fair. And if you're a reader coming in, even if there are other readers who already have access, you might have to build your solution so that you occasionally wait just to make sure writers don't starve. And like I said, that's not too hard to do. We've done that as part of a homework assignment before in this class. We talked about this a little bit. So now we've got two perfectly good synchronization mechanisms, semaphores and monitors. Which one is better? Well, this is the part that I already talked about. They're provably equivalent. Anything you can solve with semaphores, you can also solve with monitors. Anything you can build with a monitor-based solution, you can also build with semaphores. I think it's still nice to have both mechanisms around, because for me, some problems are easier to think about with semaphores, and some other problems are easier to think about solving with monitors. If we wanted to show that they're equivalent, well, for computational things, the way we normally do this, if you had two models of computation and you wanted to show that they're equivalent, usually you would show that you can build one of them using the other, and then you'd show that the other way around. And that's what we can do with semaphores and monitors. To do this proof, we would have to do it in both directions. One of the directions is a little harder than the other, so I thought we would settle for just showing the easy direction here. Your book has a discussion, and the easier direction is, if we had a monitor, we could easily build something that worked just like a semaphore. The other direction would be saying if you had to build a monitor, you could build it out of semaphores, and that is a little more involved. The easy direction is let's build a semaphore, something that works just like a semaphore, but let's build it out of a monitor. So I'm going to make a monitor. This is using our semaphore pseudocode. I'm going to make a monitor called my semaphore, and I'm going to say I want this to behave like a monitor. It's going to have 3 functions on it. Well, it's got an initialization function. When you initialize it, you give it a count that the semaphore is supposed to maintain. And I've got a field that maintains that. So it's declared up here. So whenever you make an instance of this monitor, it just remembers whatever count you give it. Down when you call acquire, well, we already know how acquire, for semaphore, we know how acquire is supposed to work. You wait until the count on the semaphore is positive, and then you decrement it. That is really easy to do inside a monitor. If you call acquire, well, since this is a function in a monitor, that automatically acquires the lock when you go in. And then while we have the lock, we'll just look at the count. As long as the count is 0 or negative, we're going to wait. And to do that, I need a condition variable. So I've got a condition variable. I called it positive here because I'm waiting for the value of the semaphore to be positive. Once it hits positive, I'm going to count on someone else to wake me up. I'll decrement the count and then return. So acquire is pretty easy to write, just using monitors. Release is how we wake up threads that might be waiting in acquire. When you call release, we just increment the count. And if anyone was waiting for it to be positive, well, as long as it's positive after we increment it, we wait for we signal one thread to let it know that it can make progress. And this, given all the stuff monitors can do for you, it's pretty easy to write something that works just like a semaphore. I kind of mentioned this earlier when I was talking about Java. In the early days of Java, you might have to write your own semaphore using Java's built-in synchronization mechanism, and this shows how easy that would have been to do. This gets us to the end of chapter 6 for our material. Let me quickly say what I think we've covered, and then if there are any questions, we can take that. We've got 15 minutes to talk about deadlocks, so we'll spend a little bit of time talking about that before we call it a day. So we started with the observation that multi-threaded code can have race conditions, and we started figuring out how to fix that, and we started with a really simple version of what it would take to fix race conditions, and that was the critical section problem. We looked at a number of solutions for that. Some of them are instruction-based, like machine instruction-based. Some of those are things like Peterson's solution, which we know doesn't necessarily work on a modern machine. And we ended up, and even then, those solutions all included busy waiting. It'd be nice to have mechanisms provided by the OS that give us efficient ways to wait for things. And that is in practice what we have, whether you're talking about semaphores or monitors, whether you're implementing in Java or C. Semaphores give you an efficient way for threads to cooperate and for one thread to wait until it has something it needs. We tried to do a lot of practice. I tried to talk us through writing or understanding a couple of synchronization mechanisms. And on, I want to say maybe all of your remaining homework assignments, that might be an exaggeration, but you'll get plenty of chances to practice this yourself on other problems. When we meet in person in class, usually it's easy to have quizzes where we can solve little synchronization problems. That's a little harder to do when we're all distributed. Questions before we finish up talking about synchronization? All right, like I said, our next topic is deadlock, and I kind of think of this as topic 3 in what is probably my favorite 3-topic series in this class. We started introducing the idea of threads, and that's a good way of getting of writing a program that can attend to multiple things at once, of getting value out of a multi-core system. And then in chapter 6, we observed, well, if you're writing multi-threaded code, you have to worry about synchronization. Threads may have to coordinate their behavior. And here, I think this builds on what we saw with Dining Philosophers. If you're writing multi-threaded code with synchronization, you might have to worry about those threads getting stuck. And that's the problem of deadlock. I'll try and give you a good definition of deadlock. It's up at the top of this slide. Deadlock is when you've got a set of threads or processes, and we'll say that's a set S of threads or processes. They're all waiting for something. They're all stuck. They can't make progress because every thread in that set is waiting for something, but they're all also holding things. So they've acquired resources that one of the other threads in the set needs. And if you kind of picture that, you can say, well, those threads are stuck forever. If they're all holding something that someone else in the set needs, but they all need something that someone else in the set is holding, then they're never going to get out of that situation. So that's bad. When our programs get stuck in a deadlock like that, just waiting for things to get better is never going to help. We're going to have to do something more decisive if we catch our programs in an error like that. This can happen all over the place. I've got a couple of examples here. A lot of times when they talk about deadlocks in processes, they talk about acquiring resources, where a resource might be a device on the system, like maybe you need to use the DVD burner or you need to use a tape drive. So a lot of these problems sound like, pretend you have a system where you have two devices. Here, let's say 2 tape drives. You've got 2 processes that both want to use a tape drive. So they go to the OS and say, let me use the tape drive. And the OS says, sure, I got 2 of them, you can each have 1. And so far we're fine. But if they then both decide they need a second tape drive, then they are both stuck. It's the same as what we talked about at the top of the slide. They both have some resources, but they're all waiting for resources that are held by the other process. So this can happen, like I said, a lot of the ways you'll hear this described is with resource allocation. We already saw this can happen in our own synchronization code, and it's really the same kind of thing. If I had 2 processes, let's say P1 and P2, and I had 2 semaphores A and B, and let's say I initialized them both to 1, let's say process P1 needs to acquire both semaphores, so it could acquire them both. P2 does the same thing, so it acquires them both, but if we just got the order of those backward, and here maybe it looks silly, but if P1 acquires A before B, and P2 acquires B and then acquires A, if these 2 processes did this code at about the same time, they would both be able to do the first acquire. But that would decrement the semaphores to 0, and then they'd both be stuck forever trying to do the second acquire. And this is kind of what happened in our Dining Philosophers, our first solution to that. We had a lot more than 2 processes, but really that was the same thing that was going on between them. So we want to be able to convince ourselves that we can write multi-threaded code and that it will be immune to the problem of deadlock, that we can plan ahead and try to make sure we don't do stupid things like this that invite deadlock. To do that, we're going to formalize the problem of deadlock a little bit, or I guess we're going to develop a little notation that it makes it easy to look at a system and tell if it's deadlocked or not. And I didn't make up this notation. It's called the resource allocation graph. It's kind of an instantaneous picture of all the resources on a system, or at least pretend all the resources, all the processes on a system, what they all have, what they're all using, and what they're all waiting for. In this notation, we're going to have, in fact, I'll bump ahead a slide because this has a better picture of my the notation. So we're going to draw resources like this. Every resource, and when I say resource, you can think of that as, that could be all the tape drives on your system, or all the DVD burners, or all the printers, or all the blocks of memory that might be available to processes. So every resource is a different kind of thing, like block of memory, tape drive, DVD burner. Every resource might have multiple instances, and that's what the little circles in those boxes mean. It might mean that you have a system that has not just 1 tape drive, but it's got 2 of them. and either is as good as another. So when you want a tape drive, you're happy to get the top tape drive or the bottom tape drive, it doesn't matter. So we'll pretend that resources have types and that each type of resource could have multiple instances. Here, R1 has 2 instances, R2 has 1 instance, and R3 has 3 instances. We're going to draw processes as little circles with usually a made-up process name in it. So here I'm pretending I've got 4 processes, P2 through P4. I skipped ahead of this last slide, so let me go back and see if, yeah, I think I said everything that was on this slide, so I don't know if we need, here are some examples of resources, kind of like I was talking about. So I don't know if we need to revisit that. All right, we got processes, we got resources. How does the system work? Well, as processes run, they get to ask for resources. And this usually means they're going to the OS to ask for a resource. So if they want to use the tape drive, they have to request it from the OS. So when a process wants to use a resource, the first thing that happens is it has to ask for it. It has to request it. And then if the resource is available, like if the OS has a tape drive that nobody's using, the OS can give it to the process. We use the word assigned for that. So a resource is assigned to a process when the OS lets it start using it. That'd be kind of like if you opened a file, you could think of the file as a resource. When you open the file, you get back a handle for that file, maybe a file pointer or a file descriptor if you're in Unix. And that's when the resource is assigned to you. At that point, you can use it. And you can use it for as long as you want. We're going to pretend when a process gets a resource, it gets to make use of that resource. It gets to burn DVDs on the DVD burner for as long as it wants. And then when it's done, it can release the resource. That's like closing a file. You go back to the OS and say, I don't need this resource anymore. The way we're going to notate this, so we've got circles for processes and little boxes for resources. We're going to draw arrows between them to show what resources processes have requested and what resources have been assigned to the processes. And we're going to call those arrows edges. A request edge, I got a picture for this. So a request edge is one like this one up here. It's an arrow from a process to a resource. Here I drew it, and I'll say this is the right way to do this. I drew it to the resource itself. Because if you ask for a resource, you don't care which instance you get. If resource 1 has 2 instances and P1 needs one of them, it's happy to get either of those. So this is a request edge. We draw that when a process asks for a resource. These other arrows, the ones that go from a resource instance to a process, those are the assignment edges. That shows when a process has been assigned a resource. So in this picture, P3 has 1 instance of R1, P2 has the other instance of R1, P4 has an instance of R2, but it wants an instance of R1. So maybe it needs both of those things to make progress. Right now, it looks like it can't make progress. If P4 is waiting on an instance of R1, well, if it's used a blocking call to wait for that, then P4 is blocked until it can have its instance of R1. Sorry, I'm just trying to decide if I had anything else to say about that. So while we've got the picture up, any questions about the resource allocation graph notation? As a system runs, you could imagine that if we were keeping up with this notation, we're drawing and erasing arrows all the time. Processes request things, and then they get assigned to the process, and then eventually the process releases it, so the OS gets that thing back, maybe to give out to some other process. The OS doesn't really keep a picture like this. I don't know what that would mean. But it does know what's in this resource allocation graph, because it seems like it would have to keep up with that. If I've got 2 instances of R1, the OS knows who's permitted to use them right now. So it's really keeping up with the assignment edges. And if P1 is waiting on an instance of R1, the OS has to be keeping up with what each process is waiting for so that it can efficiently wake up that process when it can make progress again. So we've got a way of drawing what a resource allocation graph looks at like. That lets us talk about the state of a system. Is it deadlocked or not? How are we going to use it? Well, there are 3 standard ways of dealing with deadlock on operating systems, and we're going to talk about all 3 of these. First, we're going to talk about preventing a deadlock. And as a programmer, I think that's probably our most useful way of thinking about this. It's kind of what I said before. Deadlock prevention is the idea of, can you build a system where you can know for a fact that it can't possibly deadlock? And as long as you build the system in a way that's consistent with that, you don't have to worry about deadlocks while it's running. We'll talk about that first, and again, that's what's called deadlock prevention. Deadlock avoidance, let's jump down to the bottom, because I think detection is easier to talk about than avoidance, but we'll come back to it. Deadlock detection is, can you build a system where it's at least possible for a deadlock to happen, but when it happens, you can at least notice that it has happened, so you don't have to sit and kind of hope that these programs are going to finish running. You can know when they've hit a deadlock. And then, is there any good way to deal with a deadlock after it happens, to recover from a deadlock? All right, let's try avoidance. Deadlock avoidance is the idea of, can I build a system where processes have all of the tools they need to make a deadlock? And we'll make more sense of what that means in a little bit. But as processes run, backing up a slide, as I'm keeping up with this resource allocation graph, can I think ahead as the OS? And can I try to steer processes so they never actually get into a deadlock? So I'll let them request resources when I want, whenever they want, use them for as long as they want. I'll just try to make sure they never actually cause a deadlock. And we'll save that one for last. I think it's the trickiest one to talk about. But by the time we get there, we'll be ready for it. I lied on the previous slide. I said there are 3 standard ways of dealing with deadlock. Now there's one 4th one that is by far the most popular way, at least for operating systems. Operating systems don't generally worry about handling deadlock themselves. They don't have support for catching deadlocks that when they happen. They don't force processes to operate in a way that won't lead to deadlock. I think this reflects the idea, 2 ideas. One is detecting deadlocks all the time, looking for them, trying to avoid them. Those can be really expensive, both in computation time and in resource utilization. We'll see that if you force processes to always play nice, that can waste a lot of time on resources. I think the general feeling is it's up to the programmer or the system administrator to worry about this. If you're writing a piece of code that's multi-threaded, it's generally your job to worry about making sure those threads can't deadlock. So we'll talk about various techniques you could use to try and convince yourself that you've written a program correctly. That'll start on this slide, but it'll start next time. We just ran out of time. Sorry for the power outage earlier. I'll try to, like I said, I'll try to paste the 2 parts of the lecture together, and we'll see how that goes. That's it for today, but if you want to hang around with questions, I'll be happy to take them after class.